For decades, astrophysicists tracking solar activity operated under this really rigid, basically unbreakable assumption.
Right, yeah, they thought they had the limits completely figured out.
Exactly. Like when the sun released a very specific kind of radio burst, the absolute maximum duration you could ever expect to see was, well, about 5 days.
And that was the hard ceiling.
That was the ceiling. Until August 2025, when the sun seemingly just broke its own rules.
Yeah, it really threw everyone for a loop.
Because this routine signal stubbornly refused to fade, right? It just stretched on for a mind-bending 19 days.
Which is just, I mean, it creates a unique kind of panic in the astrophysical community.
I can imagine.
When a fundamental boundary gets pushed that far out, like nearly 4 times the previous record, it indicates there is a mechanical process happening in the solar atmosphere that we have entirely missed.
Wow.
And finding out what that process is, well, it requires pulling data from basically every single piece of hardware we currently have flying through the inner solar system.
Which is exactly what we're going to get into.
Yep.
So we are pulling our intel today from a May 23, 2026 Science Daily article.
It's a great breakdown of the event.
Yeah, it details these recent findings from NASA's Goddard Space Flight Center, which were actually originally published in the Astrophysical Journal letters.
Right, so we have some really solid peer-reviewed data here.
Exactly. So the mission for our deep dive today is to explore this unprecedented 19-day solar anomaly, uncover how an interplanetary fleet of spacecraft teamed up to solve the mystery, and figure out what this means for the technology you rely on every single day.
Because it does affect you, whether you realize it or not.
Definitely. Okay, let's unpack this. Before we get into the whole massive space fleet aspect, we need to look at the anomaly itself. Like, what physically happened in space that threw scientists for such a loop?
Well, we have to look at the specific classification of the event. This wasn't just, standard background solar noise. It was what astrophysicists call a Type 5 radio burst.
Okay, a Type 4, what does that mean exactly?
So Type 4V bursts are distinct because they're produced by highly energetic electrons that get trapped within the sun's incredibly complex magnetic fields.
So they're physically stuck there.
Exactly. And as these charged particles are captured, they're forced to spiral at immense speeds around the magnetic field lines.
And it's that spiraling motion that's like throwing off the continuous radio waves.
Yeah, precisely. The physical acceleration of the electrons in that circular path radiates energy outward as broadband radio waves.
So we pick that up as a continuous signal.
Right. But under normal circumstances, these magnetic traps are highly unstable.
They don't last.
No, they degrade, or the electrons just lose their energy through the emission process, and the signal burns out. Usually takes a few hours, or at the extreme upper limit, 5 days.
Okay, so if we think about a standard solar burst, like, say, a car alarm going off down the street.
Sure, that's a good way to look at it.
Someone bumps the bumper, the alarm blares for an hour, and then the battery dies, or it just resets. It's annoying, but it's temporary.
Right, it runs out of juice.
But what you're saying is, this 19-day event is like that exact same car alarm blaring at maximum volume for nearly 3 weeks without a single pause.
Yes. That's a perfect analogy, actually.
The sheer duration implies that somebody is, like, actively out there swapping in fresh car batteries while simultaneously reinforcing the wiring so the circuitry doesn't melt down.
Exactly. And that implies a self-sustaining physical mechanism we hadn't documented before.
Because it shouldn't be possible.
Right. For a Type 5 burst to last 19 days, the magnetic bottle holding those electrons couldn't just be sitting there statically.
It had to be fed.
It had to be continuously fed with fresh, highly energetic plasma, and the magnetic containment field itself had to be unimaginably strong to withstand the internal pressure without just snapping and releasing everything into the void.
Which opens up, honestly, a massive logistical nightmare for the people trying to study it.
Oh, absolutely.
Because the sun is a massive rotating sphere, right?
Right.
And it completes a rotation roughly every 27 days.
Correct.
So if you have an event fixed to one specific magnetic structure in the solar atmosphere, and it's broadcasting for 19 days, you can't just, point a telescope at it from Earth and hit record.
Right, because it's going to rotate around to the far side of the sun and just disappear from view.
It creates a huge blind spot.
A fundamental blind spot, yeah. A single spacecraft or even Earth-based observatories, they just cannot maintain a continuous line of sight on a single solar coordinate for nearly 3 weeks.
The rotation just carries it away.
Inevitably. And if you lose visual and instrumental contact with the burst, you lose the ability to measure its intensity, its frequency shifts, its ultimate decay.
So you end up with a broken data set.
Exactly.
Then how did Goddard get a continuous 19-day data set? Like, If one satellite goes blind, did they just pull data from a satellite on the other side?
Basically, yes.
So it's essentially an interplanetary relay race, where these satellites are effectively passing the observational baton to one another to keep eyes on the target.
That is exactly what they had to do. To build that continuous timeline, researchers combined observations from a fleet of spacecraft spread across the inner solar system.
Which ones were involved?
This included NASA's STEREO mission, the Parker Solar Probe, the WIND spacecraft, and the joint ESA and NASA Solar Orbiter mission.
Wow, that is a lot of hardware.
It is. As the sun rotated, different spacecraft observed the burst as it moved into their specific field of view.
Okay, so as it leaves Parker's view, it enters Stereo's view.
Exactly. Each mission captured several days of data, allowing scientists to stitch together a complete picture.
But wait, stitching that data together can't be as simple as just, like, putting two spreadsheets next to each other.
Oh no, not at all.
Because these are vastly different machines, right? Parker Solar Probe is diving incredibly close to the solar corona, while WIND is sitting out near Earth.
Right, their instruments have different sensitivities, different noise floors, and entirely different ways of recording telemetry.
So harmonizing that data must be a nightmare.
It's a monumental task in data science. You have to account for the time delay of the signals reaching different distances, calibrate the radio frequency receivers.
So a spike on one matches a spike on the other.
Exactly. Only by layering these overlapping calibrated observation windows could they synthesize a single, uninterrupted 19-day wave profile.
That's incredible.
Yeah.
But what's interesting here is they didn't just use this relay race to record the volume of the burst.
No, they went much further. What's fascinating here is that scientists actually created a brand new technique using information from the STEREO mission to pinpoint the burst's exact origin.
But if they already had all these satellites listening to it, why did they need a new methodology to find out where it was coming from?
Well, because hearing a siren and knowing exactly which car is producing it in a crowded city are two very different problems.
Oh, I see.
Radio waves are notoriously difficult to pinpoint in the chaotic, heavily magnetized environment of the solar corona. Signals get refracted and scattered by the solar atmosphere before they ever reach our detectors.
So you might know roughly which hemisphere it's in, but not the specific structure.
Right. Identifying the exact physical magnetic structure requires filtering through all that scattering.
So how did this new technique actually cut through the noise?
They leveraged the unique positioning and instrumentation of STEREO, which stands for Solar Terrestrial Relations Observatory.
Right.
STEREO is designed to provide stereoscopic, multi-angle views of the sun. By analyzing the microscopic differences in the arrival times and the frequency drift as the waves hit different sensors across the fleet.
They could triangulate it.
Exactly. Combined with STEREO's highly precise directional data, the team essentially built a 3D triangulation model. They mathematically traced the refracted radio waves backward through the layers of the solar atmosphere.
They reverse engineered the scattering.
Yes. It's a localized radio direction finding technique, but applied on a stellar scale.
That is wild.
And they mapped the trajectory of the waves right down to their origin point in the lower corona, landing squarely on a massive magnetic structure known as a helmet streamer.
Okay, a helmet streamer. I think most of you listening are probably familiar with helmet streamers, actually, especially if you caught the stunning total solar eclipses over North America in 2017 or 2024.
Oh, definitely. They're very distinctive.
Right. When the moon perfectly blocks the main disk of the sun, those bright, glowing kind of V-shaped spikes you see extending out into the blackness of space, those are the helmet streamers.
Beautiful structures. They are colossal loops of magnetic field lines rooted deep in the sun's surface, arching high into the corona and trapping dense glowing plasma.
And they taper off into those classic pointed tips, right?
Yeah, because the solar wind is physically dragging the tops of the magnetic loops outward into the solar system.
Okay, so we know these structures hold a lot of tension, but a helmet streamer just sitting there doesn't explain a 19-day Type 5e radio burst.
No, it doesn't.
We established earlier that the magnetic bottle needed a continuous supply of fresh energy to keep the electrons spiraling for that long. So where did the fuel come from?
Well, the triangulation model revealed that the 19-day burst wasn't just happening on its own.
Okay.
It was a highly dynamic, sustained chain reaction. Scientists believe it was fueled by 3 separate coronal mass ejections, or CMEs, that erupted from this exact same region.
Whoa. 3 separate eruptions.
Yes. These enormous explosions released massive amounts of magnetic energy and charged particles into space.
But wait, hold on. If a helmet streamer fires off a massive CME, shouldn't that completely shred the underlying magnetic structure?
Normally, yes.
Right, so how do you get three massive eruptions from the same streamer without destroying the trap that's holding the electrons?
That is the core of the mystery this research solves. The three CMEs did not blow the streamer apart. They interacted with it through a process called magnetic reconnection.
Reconnection.
Yeah. As the CMEs erupted, their highly energized magnetic fields slammed into the existing field lines of the helmet streamer. But instead of shattering the structure, the field lines snapped and reconfigured, constantly injecting fresh waves of highly energetic electrons deep into the streamer's base.
So the eruptions were actively feeding the anomaly.
They were acting like localized particle accelerators. Each subsequent eruption pumped a massive new population of energized electrons into the magnetic trap.
And the helmet streamer just held together.
The streamer itself was robust enough to maintain its overall containment field. It absorbed the shock waves and kept the electrons tightly bound.
Wow.
It was this continuous, violent refueling process from those three sequential explosions that allowed the radio burst to persist for 19 days.
Okay, wait, I want to offer a specific pushback here to clarify the danger for you listeners.
Garrett, what are you thinking?
Because when we talk about a 19-day radio burst firing out of a massive solar explosion, it sounds terrifying. Are these actual radio waves hitting Earth and causing problems, or is it something else entirely?
Oh, I see. No, the radio waves themselves pose zero danger to Earth.
Zero danger.
Completely harmless. Radio waves are just a form of electromagnetic radiation, like visible light. They travel at the speed of light, wash over the Earth, and pass into the cosmos without causing any physical degradation to our technology.
Okay, so the radio waves are basically just the flash of the muzzle.
Exactly. Instead, the magnetic conditions that cause the radio waves trigger those coronal mass ejections. It's the charged particles from the explosions that we have to worry about.
The CMEs are the actual kinetic projectiles.
Right. The radio burst is the warning siren. The physical hazard comes from the billions of tons of charged plasma that the CMEs hurl through the solar system.
So what does this all mean? We understand the bizarre mechanics. A massive helmet streamer absorbing three CMEs, creating a supercharged magnetic bottle.
Yep.
And we understand the sheer ingenuity of the scientists tracking it. But we need to connect this distant solar phenomenon directly to your everyday life on Earth. Why does tracking a 19-day solar anomaly actually matter to us?
If we connect this to the bigger picture, it is fundamentally about space weather forecasting. Those clouds of charged particles can seriously interfere with satellites, spacecraft, and other space-based technologies near Earth.
Right, because our modern civilization has basically externalized its central nervous system into low Earth orbit.
Exactly. The communications networks, the timing signals for global financial transactions, the GPS grids, all of it relies on highly sensitive microelectronics flying through the vacuum of space.
And those electronics are incredibly vulnerable to the charged plasma from a CME.
Highly vulnerable. When a dense cloud of charged particles collides with Earth's magnetosphere, it induces severe geomagnetic storms.
Which causes what, exactly?
Well, a few things. On the ground, the fluctuating magnetic fields can induce massive, unexpected electrical currents in the long, conductive wires of power grids, potentially blowing out transformers.
Like the classic grid failures we've seen in the past.
Exactly. But in orbit, you have the threat of deep dielectric charging. The highly energetic electrons from the storm can penetrate a satellite's shielding and accumulate deep inside the internal circuit boards.
Oh, man.
And when that electrical charge builds up to a critical threshold, it arcs. You get an electrostatic discharge right through the brain of the satellite.
Which just scrambles the memory or fries the hardware permanently.
Yes. And there's also atmospheric drag. The energy from the solar storm heats the Earth's upper atmosphere, causing it to expand.
Right. We saw that a few years back with the Starlink deployment, right? Where satellites basically just got pulled out of the sky.
Exactly. Satellites suddenly find themselves flying through a thicker layer of gases. The drag increases exponentially, their orbits rapidly decay, and if they can't boost back up, they burn up in the atmosphere.
Which brings us right back to why studying these extreme events is so vital for space weather forecasting.
By understanding how these unusual long-duration bursts operate, scientists can better recognize them in the future.
Because if we don't understand the extreme upper limits of what the sun is capable of, we can't build accurate predictive models.
Exactly. The ultimate goal is improving space weather forecasting to protect our space infrastructure. If a helmet streamer can survive 3 CME impacts and remain dangerous for weeks, Our baseline models have to change.
It gives satellite operators the lead time they need to power down non-essential systems, right?
Yeah.
Or angle solar panels away from the incoming storm.
Yes. In a world heavily reliant on orbital tech, understanding the sun's extreme outliers isn't just academic, it's infrastructure protection.
Okay, let's briefly recap the journey of this deep dive.
It's been a ride.
It really has. It started with a routine-seeming signal in August 2025 that stubbornly lasted 19 days, blowing past the 5-day maximum.
Right.
Then we had an interplanetary relay race of satellites, Parker, Wind, Stereo, Solar Orbiter, teaming up to track it.
Using that amazing new triangulation technique.
Exactly, which led to the discovery of a V-shaped helmet streamer firing off 3 massive eruptions that constantly refuel the magnetic bottle.
Yeah.
And finally, we saw the vital importance of space weather forecasting to protect the orbital tech we use every day. So the next time you use a satellite-dependent technology like your GPS, remember the massive, invisible magnetic forces constantly at play in our solar system and the scientists keeping watch.
It really puts things into perspective, but, it also leaves us with a highly provocative reality to ponder.
What's that?
Well, since this anomaly lasted 19 days, nearly 4 times longer than the previous record, it forces us to wonder what other massive, long-duration space weather events the sun might be capable of that we simply haven't witnessed yet.
Wow, yeah.
And more importantly, whether our modern technological world is truly prepared for when the next record is broken.